So we've talked about measurement and how measurement developed in the last unit. And we talked briefly about the development of the basic ruler and how it came from, once we standardized measurement from, King Edward's thumb and foot and started cutting blocks and, standard pieces to use as those measurements, they eventually created a ruler and marked out those measurements on that ruler. So, to measure something with that ruler, they would line up the beginning end of the ruler with the one end of the object, and where the other end ended up was the length of it. So this now was closest to the 2, so this would be measured as 2 units. This was also closest to the 2, so that's also measured as 2 units. Now looking at them, they're not the same length, but this ruler is not precise enough to tell the difference between them. So to make it more precise, precision is defined as the ability to distinguish between similar objects. So they cut the units in half. Unfortunately, now both of these are still closest to 2.5. I didn't get that quite centered. Right about there looks better, right? Yeah. Both of these are still closest to 2.5. So they would still, with this measuring device, be measured as 2.5. So it's still not precise enough to distinguish between them. So we keep cutting things in half.
Doesn't the basic ruler go down to 16?
Yep.
16?
So now at this point, it looks like the blue one is slightly closer to the 2.5, and the green one is slightly closer to the 2.25. So now this ruler is finally precise enough to distinguish between them. And like I said, the definition of precision is the ability to distinguish between similar objects. The degree of precision of a measuring device is equal to its smallest division. So on this ruler, that is 1/4 of a unit, 1/4 inch, if we're measuring in inches. Now, like I said, a standard ruler goes down to a 16th or a 32nd. So that degree of precision would be a 16th or a 32nd, depending on the ruler. Even tape measures go down always to at least an 1/8, usually to a 16th. Now, if we look at these, this blue line is not exactly at 2.5. It's just closest to 2.5. But anything from here over to about here would have been measured as 2.5. So it could have been, how far off could it be? Not 1/4, well, 1/8 of an inch each way. And so that defines what we call the greatest possible error. Our greatest possible error is half of the degree of precision. So in this case, that would be 1/2 times 1/4, or 1/8 of an inch. So what that is saying is any measurement with this ruler is off by as much as 1/8 of an inch. So this is measured at 2.5 inches here, but technically that's 2.5 inches plus or minus 1/8 of an inch. So when I'm measuring that on this ruler and I say something measures 2.5 inches, that means it could be as small as 2.5 minus 1/8, or 2 3/8 inches, or as large as 2.5 plus 1/8, or 2 5/8 inches. So anything measured on a ruler is not exact. It implies a range. So we know the degree of precision of this ruler is 1/4 inch. That means the greatest possible error has to be 1/8 of an inch. So anything measured on that ruler is plus or minus 1/8 of an inch from what we say it's measured. Now you might ask, well, why don't we just guess and say that that's 2 3/8? Because we don't have a division there. If we say that's 2 3/8, we're guessing a degree of precision that isn't really there. And in most cases, it doesn't make a big difference. But there are some cases where you're doing precision measurement, precision calculations. If you're guessing that extra degree of precision, it messes up your calculations as you go. Does that make any sense? So for this ruler here, what is the degree of precision? What's our degree of precision here? Yeah, if we look at it from 1 inch to 2 inch, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 spaces. So each space, each division is a 1/16 of an inch. So yes, the smallest division is a 1/16 of an inch. So that's our degree of precision. What is that greatest possible error or possible error? 1/32. Yes, 1/2 of 1/16. Your 1/16 divided by 2 or 1/16 times 1/2. Either way is going to give us 1/32 of an inch. So it's plus or minus a 32nd of an inch. Yeah. So if something is measured, you get a measurement off there that says that it is 2 3/4 inches. What is the implied range of that? On this ruler here.
It would be 2 and let's see, 3/4 of 32 is 8, so that would be
3/4 of 32 is
what?
1.
32 divided by 4 is 8.
So
8 by would be 2 and 24 30-seconds to 2 and
you started out right, but you missed one very important step. You converted the 3/4 to 30 seconds. You got the 24 30 seconds. But then you have to
subtract plus or minus
1. So this is going to be 2 and 23 to 2 and 25 30 seconds of an inch. That's your implied range. So in your notes, so for this one, what is the possible error? Careful. Yeah, to get the the possible error, you have to have the degree of precision first. And the smallest division here is 1/8 of an inch. So the possible error is half of that, or divided by 2. 1/8 divided by 2 is 1/16 of an inch. So plus or minus 1/16 of an inch. Let's say you're given a measurement of 1 1/8 inch. Find the implied range. What's the,
That converts to 30 seconds.
you can convert 30 seconds, but what's our degree of precision here?
Degree of precision is 1/32.
That's 1/32. So what is our possible error? Plus or minus half of the degree of precision, 1/64. So this is plus or minus 1/64.
Implied range is
You turn 1/8 into
1
8/64. So
1 7/64 to 1 9/64.
perfect.
How would you say that? Like,
Exactly what you just said. The implied range is 1 7/64 of an inch to 1 9/64 of an inch. That's exactly what you would say. So I mean, you need to keep in mind the degree of precision when something is measured. And measuring something to a ruler that only goes to the 1/8 of an inch and saying it's 1 1/8, well, that could be anywhere from 1 1/16 to 1 3/16. If it goes to a 30-second like this one, however, it's 1 7/64 to 1 9/64. That's a much tighter range. Now, a lot of numbers aren't listed with fractions. If they're listed like this as a fractional measurement, you have to know something about the ruler. You have to see the ruler and see, oh, the degree of precision is this, so then I can figure out the error, and I can go from there. Yeah, from here backwards, you can know, okay, this is a 2/64 range, so it must have been plus or minus 1/64. So therefore, it's a 1/32 degree of precision.
Is it possible to have more than just a 1 possible, like that's plus or minus 1? Is it possible to have like plus or minus 2 or plus or minus 4?
Not in a fractional ruler like this. No, it's always plus or minus 1 because you're half of that degree of precision, that smallest division, which is always going to be one space out of however many divisions in a unit.
Okay.
But what if we have a ruler that's done in decimals? Let's use a micrometer or a caliper, and you get something, you get a measurement that's in decimals. Like I said, here, just giving you that measurement of 1 1/8 inches wouldn't tell us anything. You'd have to see the ruler or know that the degree of precision of the ruler is 1/32 of an inch in order to come up with that range. But if we have measurements in decimals, the range and the degree of precision and all that is implied within the decimal. Sort of. Is there a difference between these two measurements? You shake your head no. And numerically, there is not. But in precision measurement, there is a huge difference. Like I said, numerically, 4/10 and 40/100 are the same value. But
It makes a difference on the ruler, on the measuring tool.
this one up here is implying. What is the place value of that last digit? Tenths. So 2.4 centimeters. That is implying it was measured on a ruler that went down, or some sort of measuring device that went down to the nearest tenth of a centimeter, which is implying that it could be anywhere from here to here. In other words, it's implying a degree of precision of 1/10 of a centimeter. And I'm actually going to do it as a decimal. 1/10 of a centimeter, because that's the place value of that last digit. The degree of precision is the place value of the last digit. So that is an implied error of how much? What's 1/2 of that? If I take 0.1 divided by 2, 0.05. Very good. So that's plus or minus 0.05 centimeters. So if I take 2.4 minus 0.05, that's 2.35 centimeters. 2.4 plus 0.05 would be 2.45 centimeters, which is just what we drew out here. This one is implying, since it goes to the nearest hundredth, it's implying a degree of precision of 0.01 centimeter. So that's implying it was measured on a ruler like the bottom side here, where it's actually divided down to the nearest hundredth of a centimeter. And it happened to be closest to the 2.4. So that's implying an error of what? 0.005 centimeters. So then the range, 2.4 minus 0.005 is 2.395 to 2.40 plus 0.005, 2.405 centimeters. Makes a huge difference. So, and there are some people that are used to, they see other measurements reported with 2 decimal places, they just add that 0 on there. You cannot put that this 0 on here unless it means something, because it is very, very important to your measurement. Now there's a whole big discussion of something called significant digits. That we're not going to get into, because you guys don't really need to know a lot about error analysis, measurement error. If you were going to the engineering side of things, significant digits is huge. What significant digits does is it talks about when we add or subtract these numbers, how do we treat these implied errors? Because if I have a number like 5.2 centimeters and I'm adding it to 3.63 centimeters. Well, this one here has an implied error of plus or minus 0.05 centimeters. So the degree of precision is 0.1, half of 0.1 is 0.05. Well, that error here is bigger than that 3/100ths there. So including that 3/100ths in our calculation is pointless, because we've got errors that are bigger than that. So when we add numbers dealing with measurements and significant digits, a lot of times we take the least precise. This one's considered less precise because it only goes to the 10th. This goes to the 100th. It's more precise. So a lot of times when we're adding and subtracting, at least we go to the least precise and we round all the numbers to that least precise place. And then we add or subtract them. We're not going to get into that here, but it's something to be aware of. That, a lot of times you see calculations done with measurement, and you're asking, well, why did they round it off like that? Well, that's why. Is they're keeping that precision intact. Yep. Yep. Very, very much so. Yeah, very similar. Bless you. So if I report a measurement as 5.74 inches, find the degree of precision and the possible error for me. So yeah, Nate there said it. What's the degree of precision? 0.01 inch, right? 100th of an inch. Because that last digit is 100th of an inch. So then the error is going to be plus or minus 0.005 inches. We just took that degree of precision and we divided it by 2. So then if I give you a measurement of 3.876 inches, find the implied range. Perfect. The last digit is in the thousandths, so the degree of precision is a thousandth of an inch. The implied error, then divide that by 2 is 0.0005, or 5/10,000ths of an inch. So then the implied range
3.8755. Right?
Yeah.
And then it would be 3.8765.
You got it. This is 3, subtracting the 0.0005 is 3.8755. Adding it would be 3.8765 inches. What do you think? Yeah, the degree of precision actually is the total range. Because your error is half of the degree of precision, but it goes on each side. So your degree of precision would be the total range. If we were talking in terms of a tolerance, your tolerance would be your degree of precision. Your allowance is your error. A lot of people mix those two up. They say that this is plus or minus 5/10,000ths tolerance. No, that's an allowance. Your tolerance is actually the difference between your maximum size and your minimum size. So if you've got a plus 0.05 allowance, that's a plus 0.1 tolerance.
I'm starting to see how this math class ties in.
Yeah. Well, in about a week, we're going to do calipers and micrometers. So.
Yeah, we're going to be doing measuring bore and stroke and compression.
I've got very limited devices here to use.
I'm sure Rick will.
Rick goes into more detail. Once the depth gauge, once you learn the scale of how to read a micrometer, a depth gauge is the same thing. Yeah.
Handle, you have to press it, then you have to hold the lock, and then
yep.
release it, and it goes ding. But it's always fun trying to make sure it's level and not angled.
Yep.
On a V engine that's already angled.
Well, a lot of them actually have a T on them that you can just set on top of the.
Oh,
If you've got the plain block, you can set it on there to level them out.
yeah, our school didn't have all these miniatures, so they just sent the old hand tools. It's all good. But yeah,
Somebody walked off with my caliper last year, so that was my own caliper too. Darn it! It was a cheap one. It was only a $30 one, but still. Page 170. I was wondering why that was taking so long to write. Page 173, exercise 4.2, 1 through 29, the odd. It goes over this stuff.